Well, good afternoon. This is 2:03 on a Wednesday afternoon, the 25th of January, 2017. This is time for Math 238, and right now I'm the only one in the room, so I don't know where everybody is. I think I'm going to turn on the light. I thought it would be enough light coming in the window, but it really isn't. Gotten a little overcast this afternoon, so it's harder to see the book. So we'll see if anyone comes in. I'll rearrange the lights. Okay, my memory was we were on example 7, or getting ready to start example 7 in the section 1.1. I wish there were people here. I'd ask if there were any questions over what we've covered so far, but haven't heard any. Now, I did see that a student had added the class, okay, and another student that I thought was going to be in the class isn't showing up anymore. And then I just had another student in my 227 class ask if she could add. I said I didn't know she'd have to check at the registrar's office. So we may have 1 or 2 or 3 additional students that we haven't seen yet, but the 3 people that I have seen, none of them are here either, so hopefully they'll be coming in. Okay, one was not here this morning for his morning class, I don't think, so he may not be coming back this afternoon. He wasn't here this morning. Yeah. Nope. Yeah, he was here this morning. Yeah, so, okay. All right. So anyway, let's get started on example 7. Here's a function, x. Oh, let me get the pencil, pen color changed. Okay. Here's a function, x equals c1, some constant, cosine 4x, and some other function x, I wish they'd have given a different name or something, well, no, not necessarily, equals c2, sine 4x, okay? Where c1 and c2 are arbitrary constants or parameters, both are solutions for this linear differential equation. X double prime plus 16x is equal to 0. Okay? Now, they don't say exactly what they want you to do here yet. They just start talking. But what you would normally do is verify that these two do work. Okay? So for the first one here, and that's why I wish we'd somehow had different ways to name it, this would be x prime is equal to, and you take the derivative of that. I know derivative of cosine, well, c1 is going to be there still, that's just a constant. Okay, derivative of cosine is a minus sign for x, but then the chain rule has you with a 4 in front. So that is, x prime is equal to negative 4c1 sine x. Now x double prime would then be the negative 4c1 is still there. Actually, I'll regret doing that. Let me for right now say the negative will still be there. The c1 will still be there. Keep in mind there's a 4 there. I didn't write it yet. Derivative of sine is cosine 4x, but then you have another 4 to chain rule it through. So you had a 4 before plus times another 4 is 16. C1 cosine 4x. Okay? Now you can take this and plug it back up here, and you see that negative 16 C1 cosine 4x plus 16 times C1 cosine 4x from your definition of x up there, sure enough, they add to be, those two terms had to be 0. Do the same thing over here. X prime is equal to, and that'll be a C2 cosine 4x, derivative of cosine is cosine, chain rule, you get a 4. Okay, your x double prime is equal to, and I'll put the C2 in there, you know it's still going to be there, derivative of cosine is minus sine, okay, 4x, and then chain rule, you get a 4. 4 times the 4 you already had is 16. And sure enough, when you plug that in, x double prime is minus 16 C2 sine 4x plus 16 times your x, which is C2 sine 4x. Those, of course, add to 0. Okay. So both of those are solutions. Okay. What the other, I guess the thing they're getting at here is that what if you did the sum of these two functions? Okay, not just list them separately, but x equal C1 cosine 4x plus C2 sine 4x. And then you were to treat those as one function, and sure enough, you term by term, you do exactly what we did before, and you'd find out that you get exactly the same result. So, it is straightforward to verify that the linear combination of those two solutions, which would be some arbitrary constant, but we already have arbitrary constants, of the two parameters family, x equals C1 cosine 4x plus C2 sine 4x. I'm sorry, these are t's, aren't they? How did they get from x's to t's? Oh, I wasn't paying attention. That's what they started with. Here's a function, and I was thinking this looks so strange. Now I see why it looks so strange. Sorry. These are t's here. So these will be t's here. Okay. These will be t's. Okay. 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 Yeah, now this is making more sense. Okay. Now, what you have to watch out for here, and this is why one of the deals here, when you're doing the primes, you don't see what you're taking the derivative with respect to. Of course, it's with respect to the the independent variable, but it's not real clear. But here, x is a function of t, so therefore when you're taking x prime and x double prime, you have t's in there, and then, yeah, so I just wasn't paying attention to it and wrote that in. So anyway, the sum of those, C1 cosine 4t and C plus C2 sine 4t, is also a solution of the differential equation. Okay? Now, here's yet another example. I think I'll erase everything on here. Example 8. Actually, I had both of these marked. I'm just assuming that example 7 is where we left off last time. That's where I remembered it. So anyway, we'll look for that. All right, here's a one-parameter family of quartic monomial functions y is equal to c, y is equal to cx to the fourth. Okay? It's an explicit solution to the first linear first order equation xy prime minus 4y is equal to 0. I'm so glad you're here. I hate talking to myself. Okay. All right. Let me turn on the projector. I was recording stuff, but I wasn't projecting it because no one here to see it. I'll flip the lights here. Is Michael coming back? I was saying earlier, it was on the recording, we've had someone add to the class since the beginning of the term. She wasn't on the roll the first week or second week, but she was on the roll the first week when we went to do attendance Friday. She was on the roll, so she must have added sometime. And one of the people that was here that was on the roll isn't on the roll anymore, so I don't know if he's coming back. And then just today in my 227 class, I had a student ask if she could add the course. I said, I don't know if they'll let you in the registrar's office, but it's okay with me if you do. So we may have yet another one coming in. But I've only seen 3 people so far, but there's 2 that have been on the roll at some point or another I haven't seen, and 1 person who may be adding to the roll that I have seen in another class, but not in this one. So, yes, yeah, okay. Sorry about that. When someone came to the door, I paused the screencast-o-matic. I forgot to add it back. So, a little bit of a gap there, but this is what we were doing in that interval. Okay. Now, so we verified it. Now, I'm trying to, I don't buy their picture here. Oh, no, I see it. Okay. The A part of the graph, oh, you don't have your book yet. Okay. I'm going to try to draw, well, let's see. Actually, I do have a graph here, okay. What I'm going to graph here is, wait, this one. Y is equal to cx to the fourth. And I'm going to have c equal 1. So I'm going to plug in y is equal to cx to the fourth. Y is equal to cx to the fourth. Okay. Now, in order to do it like they do, I probably should go to blue. It looks like they sort of use a light blue, so I'll use that one. So give me some points on this one here. This is the light blue one. When c is equal to 1. Sorry. Second? I can't hear you. Yeah, just pick some points, yeah. Okay. X equals 0, what would you get? 0, 0. Perfect. Now, let's see. How do we want to scale this? What's that? Doesn't matter, but wait just a second. Let me think. I want to ask you a question. You want to use a 1-to-1 scale, or you want to use, the X scale can be different from the Y. The X's are going to stay pretty small, and the Y's are going to get very big very quickly. So you can use, let's do the Y scale of, I'm going to go back to black for this scale. Let's do 1, 2, 3, 4, 5, 6, 7. Still not going to get too many points on here. But on the X scale, you want to use 2 for 1, 3 for 1. Let's do 3 for 1. Is that okay? So that would be 1, 2. Negative 1, negative 2. There's a reason for this madness here, but hopefully you'll see it. All right, let's go back to light blue. Okay, you gave me 0, 0. You want to use plus 1? Okay, when X is plus 1, what is your Y? 1. Got it. So 1, 1. And when X is, what you want to do next? Minus 1 or plus 2? Minus 1. What would your Y be? 1 again. Good. And when X is equal to 2, you're off scale. Big, yeah, 16, exactly. So by 2, we're already way off scale. So basically, here's what your the function looks like. It's a big, broad parabola. It's not a parabola, but it's sort of a parabola-looking thing. That's what C is equal to 1. Okay? Now, they're going to choose another C. They're going to use Y is equal to minus X to the 4th. There's another one. C is equal to negative 1. Okay? Pick me some points for that one. 0, 0. Well, same X's, that'll be fine. X equal 1, what would the Y be? No, you're going to negate that then. You raise negative 1, I mean 1, yeah, okay. So that'll be a minus 1, whoops, yeah, minus 1. This will be a minus 1. And next will be a minus 16. So here you have the flip side of that. You just negated the whole function. And Nigel decided to show up. And it looks like De Silva is going to be adding the class. And that's going to be KG do Johnny. I'm going to wait and see if she does show up. I think she will. All right, so here are two solutions. This is for C equal minus 1, and the other was C is equal to plus 1. Okay? Two possible solutions. You can put in different C's, you'll get different answers. Of course, you put in a 0 and you get 0. That's not very interesting, so don't put it in 0. But put in any other C, and you'll get it. If they're positive, they're going to be up there. Negative, they're going to be down here. Okay. Now, the blue and red curves, those I just did, are graphs of those two functions corresponding to the choices of that. But you could also now come up with a piecewise defined function. I think I'm going to give it a different color. What color would you like it? Green? I'm going to give it the dark green, I believe, because I think it'll show up better. Here is a piecewise defined function. Y is equal to negative X to the 4th when X is less than 0, and X to the 4th when X is greater than 0. Now, really, technically, one of those should have an equal sign under it. I really don't care which one. I think I would put it under this one. Okay? Now, what will that one look like? Down here, it's going to follow the red curve for all x's less than 0 And then up here, it's going to follow the blue curve for all x is greater than 0. Okay? So, you could have a piecewise defined function, especially since these two meet at 0, 0, that they could come up and do this half of this one and that half of that. Now, if for some reason there wouldn't have been a meeting there, like they were separated, like say your secants and cosecants, or something like that, it will not be at the same point. Yeah, that won't work then because it wouldn't be a continuous function. But this piecewise defined function, it worked perfectly well. Okay? That's the green. Okay? So, the one other little blurb they have here is this one. Systems of differential equations. Up to this point, we have been discussing single differential equations consisting of one unknown function. Sorry. But often in theory, as well as in many applications, we must deal with systems of differential equations. A system of ordinary differential equations is two or more equations involving the derivatives of two or more unknown functions of a single independent variable. For instance, if x and y denote the dependent variables, t is your independent variable, then a system of two first-order differential equations such as this. I think I'll go back to my white page. Okay? I think I'll clear this white page because I don't think we need that anymore. Goodness, I don't know why my head's clogging up like crazy. Here is your system of equations. Let's go back to black for now. I don't think I don't need to graph any. Okay. dx dt is equal to some function f of t, x, and y. dy dt is equal to g of t of x, t, x, and y. Okay. Now, a solution for a system such as this is a pair of differential functions, okay? Pair of differential functions, x is equal to some phi of t, and y, or let's call it phi1 of t, and y is equal to some phi2 of t. Okay? Defined on some, common interval that satisfies each of the systems on that interval. Okay? Now, here is sort of a broad analogy. It doesn't fit in every case, but it's kind of like this is a function. It's a derivative, okay? But it's a function, and it's some function of x, t, and y, okay? T, x, and y. Here, your y is a different function, okay? It's a function of t, x, and y, okay? This is a differential derivative. Those are both, and that gives you those are both functions. Now, what solves that is some x as a function of t, some x, a function, that x is a function of t, and that's your phi1. Y is another function of t, phi2, that coexist on the same interval I. Okay? These would be how you solve this. because if you were to write this as a differential equation rather than a derivative equation, you would have dx equal f of x, y, t, x, and y times dt, okay? And if you could separate out the t's, leave the t's here, the x's here, you still got y's in there, but hopefully y is a function of x. It doesn't say that, but if you could reduce it to that. And then the same thing here, you still got some x's mixed up in there. But if your x is going to be some phi of t, your y some phi2 of t, then this can solve that system of equations. And what I was going to suggest to you, this was sort of like, not a great analogy, but I'm not even sure it's worth the analogy. So yeah, we'll just leave it like that. That's all they say. I thought maybe I could add something to it. This book, unfortunately, does this a little too frequently. It introduces something and then just lets it hang there and doesn't really do anything with it. This is such a case as that. I thought maybe I could do a little bit. You in? Good deal. All right. They do have these blurbs, they call them remarks at the end of the sections, and they are worth a look, but last time I taught it, I tried to go over things, but again, they seem like they just sort of muddied things up without making anything much clearer. So I've decided not to do it. Well worth your read. See if it means anything to you. It certainly hits some nice points and stuff, but I don't know if it adds a lot of clarity to what we're doing. Take a look at it and see. Now, there is one thing. There's a new term introduced there. I think it's new. It's called a general solution, okay, of an ordinary differential equation. And it's kind of like what we did in the previous example, or maybe one prior to that, where we had two specific solutions, and then we did a linear combination of them, and that also was a solution. If you've included all the solutions that could exist, linear combinations of the others and stuff, then you have what we call a general solution. That is as opposed to, and we talked about this a little bit earlier, specific solutions, which are independent of the integration constants. They are just specific solutions. Again, they mention it, but don't really follow through in it. But just to remind yourself for later when we see that term, you've seen it already. So homework exercises here, we're in section 1.1, we just finished it. Any of the odds 1 through 7, do number 9, do either 11 or 13 or both, 15 or 17 or both, do number 19, do either 21 or 23 or both. Do 25. Do either 27 or 29 or both. Do 31. Okay, 20, 31. Either either 33 or 35 or both, do 37, And then the discussion problems, generally, I would say they don't have all these answers in the back, but they may have some of them. Let me just take a look and see quickly. Through 37. No. They don't even have 37. Okay. Okay. So, anyway, you can look at the discussion problems and read through those, think through them, but don't get too wrapped up in them. However, when you have those, I see on page 12, number 47 talks about the folia of Descartes. So since his name's here, Descartes would be a legitimate paper topic. Who he was, what he did, what he contributed to differential equations, that kind of stuff. But then also, if you didn't want to just write on him, what is this folia of Descartes? How did he discover it? What does it do? What does it mean? And you can work on that as well. Okay. All right, I think we're ready for 1.2. Okay. 1.2, the title is Initial Value Problems. And quite often we'll call these IVPs, Initial Value Problems. Okay. Now, they will refer to this sum, so I'm going to write it down, though I'm used to doing this sum, but I don't find it particularly helpful in differential equation class. If it was a fairly advanced science course or perhaps engineering and stuff, you might write equations like this, but it's not particularly, to me, clear to how you were going to do it here. If we were asked to solve this, the nth derivative of y with respect to x superscript n, if this was your differential equation, asked to solve some function of x, y, y prime, y double prime, dot, 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 all the way up to y n minus 1, derivative of y with respect to x, the n minus first derivative of y with respect to x to the n minus 1. Okay. This is a fairly abstract, and that's why they use it. It's a very general expression. Basically, your nth derivative is a function of x, certainly, that's your independent variable, and then y's and all your other derivatives of y up to n, but not counting n, up to n minus 1. Okay? That's a general way of expressing it. You can't do much with it because it's so general, but they like using this term. Now, if you did have a differential equation like that, typically you would have some conditions on it. Here would be typical conditions. Y at some x0 could be y0, say. Okay? Again, these are very general. And then we'd say y prime at some x0 would be some y prime 0. Whoops. Should be smaller. Okay? I'm sorry. They don't call that y prime 0. They call it y1. Okay? again, you can call them anything you want to, but to be consistent here, y1. Okay? And then continuing, y double prime evaluated at x0 would be y2. And you continue that process until you get y to the n minus 1, the n minus first derivative of y evaluated at x0 would be y sub n minus 1. Okay. There is your differential equation. Now, I'm going to make another sort of analogy here. If you've noticed what we've been doing, before we had a line like this here, typically this would produce a set of n parameters. Okay? You would have, say, some function of x's and y's plus some, C1, P1, plus the C2, Phi2, plus the C3, Phi2. Yeah, you have those. That is sort of like your indefinite integral. Now, it's not the same thing, but it's pretty close. Remember, if you were integrating, but you didn't have limits on it, then you were going to come up with C's, constant, plus some constant. Well, when you're doing differential equations and you've got derivatives up to the nth derivative, then you're going to have a constant for every one. You have a constant for your y and then each of those, so it's another n constants. Now, when you have a condition like this, you've got some value of x where you know everything. You know the y value there, you know its slope there, you know its concavity there. You know everything that you want to know about it at that point. Well, that's kind of like your definite integral, okay? And a definite integral, you remember you go and evaluate, you don't have any c's anymore. So when you have this kind of expression, you're going to have a number of c's according to how many different y's or y primes that you have there. But if you have this, it's kind of like you do have values. If this is a starting value, then quite often we call that an initial value. Now, it doesn't really have to be a starting value. It could just be any old value, but you know everything at that point. Then those are usually called initial value problems. Now, you will have some others, and I'm not sure when we're going to hit these, but just for the reference. You might know the y's at x0, and you might also know the y's at some other x, like x1. Then you sort of count those as boundary values. And that's a different kind of problem, boundary value problem. Now, you'll need as many conditions as you have constants in those forms. Okay? So, notice here you have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. 1, 2, 3. And by the time you get to this one, that would be your nth one. You'd have to have n conditions, so you wouldn't have any of those n constants that you'd have there. Okay? If you had boundary value problems, they don't always work that way, but usually you would need at least as many boundary value things, like maybe y at x0 and y prime at x0, and then y at x1 and y prime at x1. That would be 4. So, now we're not doing those, we're just doing an initial value problem. This is what we mean by initial value problem. It's an nth order initial value problem, okay? And you call those conditions there your initial conditions, your ICs, okay? So, first thing they really hit here is a geometric interpretation of these initial value problems, okay? Now, we're just going to do a first order differential equation. I think I'll leave that up for now. Let me see. Nah, maybe not. I was thinking this wasn't going to have that much writing to do, but it probably will have. Oops, that's not what I wanted. Get rid of that. That. I got to get my pen back. Okay, now we're back. So here's what we got. dy dx is equal to some f of xy. Now that sure enough fit what we had before. This is the first order derivative, so you don't only have f of x, y, you don't have y prime because that's already here. So x, y, okay. Now, if this is an initial value problem, it needs to be subject to y at x0 is equal to some y0. It only needs one constant. And if you think about this, because this is a first order equation, so you only need one condition. That's your initial condition. Okay? Now, if you had, on the other hand, something like this, d2y dx squared, second order differential equation, this is some function of x, and how far would we go? Y and y prime. Okay, very good. Okay, where y prime is dy dx, by the way. Okay, what would be the required initial value problem, initial conditions here? Y at x0 would be y0, and y prime at x0 would be some other function of y, some other value of y, y1. Okay. So the first of these is a first order differential equation that has one boundary condition, one initial condition. The second is a second order differential equation, and so therefore you have to have at least two initial conditions, one for y and one for y prime. Okay. Now, I know that none of you have your books. Good. When we were doing the parameters, before we had initial conditions, you would only have a single parameter system here, okay? So you plug in different values of C or whatever, and that would give you your solution, okay? Solutions, one different one for every C. This tells you you're going to be on one of those lines, okay? It gave you a family of curves. This puts you on one of the curves, okay? This one would be a two-parameter system that you would have had to have two independent parameters there. So you have to have two conditions, so you don't have either of those. So that's sort of what they're getting at. And it tells you which curve would be fitting. So let's do example 1, which is actually refers back to an earlier problem, I think. Problem 41 in one of the homework exercises in the first sections. It says you were asked to deduce that y is equal to cx. I can't write. C e to the x. Okay? Is a one-parameter family of solutions to the simple first-order equation y prime is equal to y. Okay? And this will work on the interval from negative infinity to infinity. In fact, it works for all real numbers. That's what that means. Okay? No limitations on it. If we impose, okay, all right. I want you to sort of imagine what this looks like. Okay? If C were 1, that's going to be the easiest one. C is equal to 1. What would be your solution? It's going to be y is equal to e to the x. What would that graph look like? Good old exponential curve. Now, if C were 2, it's going to be lower here, go through here, and go up faster here. Okay? If C were 1/2, it would be more gradual here and more gradual there. Now, if C were -1, then it's going to come and do this. -2 would be sharper, and -1/2 would be not as sharp, and so on. So you get a family of solutions, depends on what the value C is. Okay. Now, what if they gave you this initial condition? Rather than coming up with a family of solutions like this, what if after they gave you the differential equation, they said, and y at 0 is equal to 3? Okay? Well, what you would do then, that's your family of solutions. Plug in, plug in. Now, what does the 0 stand for? That's your x value. So this is a y, but the y is 3. 3 is equal to c e to the 0th power, right? What's e to the 0th power? 1. So this says c is equal to 3. So which one of those curves did we have? Remember I said we had e to the x, e to the 2x, e to the 1/2 x, e to the 1/2, yeah, x, would be e to the 3x. That's the one that's going to give it to us, okay? So our solution then would be y is equal to 3 e to the, I'm sorry, I was saying e to the 3x, 3e to the x, okay? I was doing a different problem, e to the cx. This is ce to the x. So this would be 3e to the x, okay? Everything would be elevated, okay? E to the x would be here, 3e to the x would be, every one of the values here is 3 times the value before. This would be at 0, 1, this would be at 0, 3, okay? So yeah, it would be a parallel curve, you might say, going up there at 3, okay? And then you would not need any more c's. That's the only value of c because this initial value problem said it has to go through that point. Okay. Now, the b part. Now if we demand that a solution curve pass through the point 1, 2 rather than 0, 3, you would take the same thing that you had before. You're requiring it to pass through 1, was it 2 or -2? 1, -2. Okay. Yuck. Okay, now you say the y value is -2. That'd be -2 is equal to c e to the first. So, c is equal to -2 over e. That would be the value that you would have, okay? Now that's just one way of expressing that answer. No, that's exactly, they write it this way, -2e to the -1, yeah. C would be that, okay. That would be your solution. You don't need a family anymore because that initial condition gave it to you, okay? Now that one, because you have a negative 2 for y, that's going down here, okay? E to the minus 1 I said that wrong. That's not a minus 1. Yeah. Yes, a positive 1, sorry. I was wondering, where did that come from? It's, no, it was a minus 1. C is equal to e to the minus 1. Yeah, C is e, yeah, that was right. Because you divided both sides by e, yeah. Thought I was right there. Okay. There it's not. Wasn't working. But then it did. Okay, so that would be it. Now, the minus 2 flips it over here, but also the e to the minus 1, that changes the curve completely. Yeah, that's just a number. Yeah, that's just a number, e to the minus 1. So this is just a number, but it's a negative number. E is about 2.7, so e to the minus 1 would be about something around 1/3. So this would be like 2/3, negative 2/3. Well, that's just going to be a curve down here. Go back and put it in there. That would be y is equal to negative 2/3, or 2 over e. I like this one better. E to the x, that would be 1 that goes down this way. Okay. And it still works. It's just because you have a negative coefficient. It moves it down there. I wish you had your book. You could see these curves on it, and it would make more sense. All right. Now, that last problem we did on an interval from minus infinity to infinity. We may not be doing them all that way. In fact, in problem 6 in exercises 2.2, which is way in the future, you'll be asked to show that a one-parameter family of first-order differential equations has a certain solution. Okay. All right. Here's what. Let me erase these. Okay. There. Now, here's your ordinary differential equation. Y prime plus 2xy squared is equal to 0. Now, time out. This is for your benefit, but also to sort of help bring the Silva up. When we have a differential equation, we classify them 3 different ways. Remember what 3 ways these were? The what? Okay, yeah. The type, and that's ordinary or partial. Okay? The linear or nonlinear, and the order. Okay. Some of those sound alike, but they're meaning different. What would you say this one was? Okay. It is an ordinary differential equation because these are not partial derivatives. The prime stands for ordinary derivative. That's what we mean. Partial derivatives we haven't gotten to in Cal 3 yet. Huh? Say again? No. It's first order because its maximum derivative is the first derivative. So it's an ordinary differential equation, first order differential equation, but nonlinear because the y is squared here. Remember, the requirement for it to be a linear differential equation, all your derivatives and all your y functions, not the x's, could not be powered like this one, and they couldn't be multiplied by each other. In other words, you couldn't have a y prime times a y, or a y prime, or y prime y double prime. You know, you couldn't have two of them multiplied. That makes them nonlinear. This part looks like it could be linear, but this happens right. Now, if this was 2x squared y, that would be linear. The y's are the things that can't have an exponent more than 1. All the derivatives of y. Now, that's a prime. That's not a 1. Okay, that's a prime. But that's a 2. That means y is raised to the second power. Okay. So, just a little bit of review there. Okay, now, because it's a first order differential equation, it only needs one parameter. And here's what the solution is. Now they're just giving it to us. They didn't say how they got it. Y is equal to 1 over x squared plus c. There's your parameter c. Okay. Now, we could verify that if you really want to. So you have an idea what we're talking about with verify. How would you go about verifying it? Not going to be particularly pretty, but we can do it. How do we do that? Okay, you take the first derivative here because you got to have it there. Y prime would be equal to. Now, if I were really going to verify this, and this is the part I really don't like, I think I would write this as the y as x squared plus c to the minus 1. You could do it with with quotient rule. I think it's easier to do it this way. So what's your y prime? Minus x squared plus c to the minus 2 times chain rule 2x. Okay? Now I'm going to write that back in denominator form like the original was. That would be a minus 2x over x squared plus c squared. Said it wasn't going to be pretty, but we can handle it, right? Okay. So let's see if indeed this solution with that first derivative fits in that equation. This is how you verify that it works. Well, this is your y prime right there. So minus 2x over x squared plus c squared, okay, plus 2x, and what's your y squared? Well, here's y squared. Here's y. You got to square that, so 1 squared is 1, and x squared plus c squared is x squared plus c squared. Is that equal to 0? Yeah. Right? So we just verified that works. This problem didn't ask us to, but I thought not a bad review. So, yes, that does work. That means this is a solution for that differential equation. Okay. Now, what if the initial condition for this differential equation was this? Just saw it, there it is. Y of 0 is equal to 1. And by the way, that solution has c's in it. You pick out different values of c, that's going to give you different curves. These are going to be curves that look something like that, but going to be some strange looking curves, but they would be those curves, okay? But what if they told you y of 0 is equal to 1? Well, then you plug that into your equation here, this equation. So what's your y value here? Y is equal to 1. Okay, so that's going to be 1. 1 is equal to 1 over, and what's your x value? 0. 0 squared plus c would just be c. Figure out what c is. That's pretty easy, isn't it? Multiply both sides of the equation by c, and you get c is equal to 1. So we go back and plug in. Y is equal to 1 over x squared plus 1. There is your solution that fits that initial condition. You no longer have a c in it. You had a c, but the initial condition wiped it out. Okay? Told you which c to put there. C is equal to 1. Okay? Now, if I had written the problem right. How am I doing this today? It said, what if the initial condition was y of 0 is equal to negative 1? Okay, sorry. Then you would have put a minus down here. M for the c. So that would have been a minus 1. Okay. Wait a minute. I didn't... no. Let me start over. Okay, let me... with the correct initial condition. I think I was okay there, but let's do it again. Okay. All right. Yeah. So y is negative 1 here. So you go up here and say minus 1 is equal to 1 over x squared plus c, right? Oh, but x was 1. X was 0, so that's just c. Okay, sorry about that. That's 1 over c. So that tells us that negative c is equal to 1, which tells us that c is equal to minus 1. So now we go back to our solution and say y is equal to 1 over x squared minus 1. That would be the solution we have here. Now, but wait a minute, team. We may have a problem. This isn't good for all values of x. This is only good for certain intervals. Why? This has limitations. What can x not be? Second, the denominator can't equal 0, so x can't equal 1 or negative 1. Okay? So this would only be good, this solution is only good on an interval minus infinity up to minus 1. That would work. Or it would be good from minus 1 to 1. That would work, or it would be good from 1 to infinity. But guess what? It can't be good for all real numbers because negative 1 and 1 cannot be on it. So you have to specify what interval this is a solution for because this requires negative 1 and 1 to be taken out of circulation. So it's only good on this interval, on that interval, on that interval. Because it can't be, you cannot have an interval that includes minus 1 or plus 1. So any interval or subinterval of any of these will be fine. 0 to 1 would be fine. 3 to 5 would be fine. You know, negative 15 to negative 2 would be fine. Anything that's within that, but you couldn't do negative 2 to 2. No, that would incorporate both of those not defined. So you have to specify an interval on which that is defined. Okay? Before we've sort of been taking for granted that we knew all real numbers. No, that one is definitely not. Okay. Okay. They do show some pictures in the book, which would be perfectly fine to do. They show the graph of this, and I'm not going to graph it for you, but I'll show it to you. Okay? See, you can't have a value of -1 or 1. Over here in this interval, this is what that function looks like. And the middle interval here is that. And in this interval is that. So those would be the places you have to specify. Where are you, Waldo? Figure out where that is. You can't cross one of those not allows. Okay. Let's now look at a second order initial value problem. Example 7 that we did do, we saw that, we did it today in fact, x is equal to C1, I think it was before y'all got here though, okay, C1 cosine 4t plus, okay, C2 sine 4t. Okay, two parameter family of solutions of this differential equation. X double prime plus 16x is equal to 0. Okay? Now, it says find a solution of the initial value problem, that was this, with the condition, same as that, with this condition, these conditions. Second order, you need two conditions. X at pi halves is equal to -2, and x prime at pi halves is equal to 1. Now, this is kind of why I don't like calling this an initial value problem. Because when I think initial value, I would think t equals 0, initial value. But no, this is a t equal pi halves, or pi halves. So it's, oh no, don't tell me. It is that time, isn't it? Okay. Yeah. You want to just pick up with this next time right there? Okay. We will. We'll start this one over. I won't start griping about it yet, but we have already done that. So we'll do example 3. Okay. What this means, let me mark the page here. Exercise set 1.2, do number 1, do either 3 or 5. Do either 7 or 9. And by the way, you could do both on these. Okay, wait a minute. Let's just do 1 and 3 or 5, because 7 and 9 are second order, and that's the one we were just going to do. So we'll do that after we do where we just left off. Okay, good deal. Good to have you in the class. Did I mark you here? Let me see. No, I didn't. All right. We still haven't seen, I just put Antonisha here, not you, okay. Antonisha hasn't come here yet. Okay. We've seen Matt, but he's not here today. And we haven't seen Charles Jennings from the beginning. So I don't know if he's going to come back or not. All right, good deal. We will